Okay, so we have already established the idea of um, the electric potential, that it was equal to the change in potential energy per charge, or the negative of the amount of work done per charge, which did turn out to be equal to this value for a point charge, where the potential was positive if Q is positive, and the potential is negative if Q is negative. It also depends upon your distance from that point charge. But then in a more general sense, we also worked out that the potential was equal to the negative of the integral of the dot product of field strength and the path that you have followed through the field. And now we want to go on from that notion about the potential from a point charge and find the potential for 4 point charges. That here they are, and I want to know the potential at this point P in the center of that square. And we are so pleased that once again it is a matter of superposition. That all I have to do is put in the value for that charge and the distance from that charge, and that's the potential from charge 1. And then I'll put in the value of charge 2 and the distance from charge 2. That's the value for charge 2, and I'll add them together. And so you would do a discrete summation of those three potentials from those three to get a value there. And I would ask you to see if that makes sense by actually doing it. So you put in these values, and D is equal to that. You're going to have to do a little Pythagoras to get the distance, and you crunch out for me what the potential is there at the center. Please note that potential is a scalar, so it's not going to have any direction when you get there, and it's not like potential in one direction cancels potential in another. But potential from a negative charge will work in the opposite direction to potential from a positive charge. So you work that out. Put it on your worksheet. And then just as a tease, what if instead of 4 discrete charges we had a continuous distribution of charge? What would you do then? And obviously, I hope obviously, what you would do is break it up into the equivalent of a bunch of point charges. A continuous distribution of little point charges dq, each giving rise to a infinitesimal of potential dV. And then you'd add up all of those infinitesimals dV to get what the potential is. You would add them up continuously. And then dV, of course, is equal to 1 over 4 pi epsilon, the charge, which is dq, divided by r. So we treat it like point charges and then do the continuous summation of all of those infinitesimal point charges. But that is not where this lecture is going. That is a pre-taste of what is coming. Here you have again a distribution of point charges. There are 12 of them, and they are laid out symmetrically around this circle. So these two are diametrically opposite, and these two are diametrically opposite. It doesn't look like I did a very good job, but they're supposed to be diametrically opposite each one. That let each of those 12 have a charge q, and the radius of this circle could be r. So tell me, for this distribution, what is true about the field at the center? What value does it have in terms of q and r at the center of that circle? Put that on your worksheet. And also, what is the potential at the center if you have 12 charges q, all at distance r from this point? What is the potential at the center? Put that on your worksheet. And then we take those 12 point charges and we slide them along the circle so that they get bunched up like this. You cannot give me an expression for the field at the center, but you could talk to me about its magnitude. What kind of magnitude does it have? And its direction. However, you can give me a value for the potential at the center here. Thus, concretizing in your mind the advantage of potential being a scalar. We move on. Now we are going to start to go through all of the arrangements of charge that we looked at in chapter 22 using Coulomb's law, and then we looked at several of them in chapter 23 using Gauss's law, and in each case, in 22 and 23, we were looking at the electric field. But we now know that electric field has a relationship to electric potential. But at any rate, we're going to go back through all of those arrangements and talk about the potential for each of them. And we start with the dipole. Hopefully you remember what a dipole is. And now I drag it onto the screen. It is a pair of charges of equal magnitude but opposite sign. Di2, a dipole. And then there was also the distance, the dipole distance, which was the distance between the two, and the symbol for that was the lowercase d. Now, I would like to know what the potential from this pair of charges is at some point in space. When we dealt with the electric field, we were stuck with talking about the electric field on the axis of the dipole. But potential being a scalar, we do not have the same problem. Well, let's get this out in front. Let's see if it's still, no. Come on, come to the front. There we go. Okay. I'm looking at some point P, and this time I don't feel constrained to be on the axis. Any general point in space, and it is at some location relative to those 2-point charges. What is the potential at that location P? And again, what we're going to do is to take, oh, you behave yourself. There we go. I'm going to take those two, and I will find the potential for each one of these individually and then just add them up with a discrete summation. So here you go, and what you have is this charge, Q, at a distance r plus, and let me put that on here. We'll put it on in brown. This is r sub plus, the distance from the positive charge. And for this other one, the potential is going to be, well, the charge is a negative Q, and for r, that is r minus. And by r minus, I mean the distance of this point P from the negative charge. So there you go. It's not seem very workable yet, but we're going to get there. Behave yourself. Sorry, little technical difficulties here. Okay, let's just squeeze you smaller. No, I can't squeeze you small enough. Okay, now I can drag this onto the screen. Now I need to drag you back again. So awkward. Okay. What I've done is to, oh, go away. I've found a common denominator of those two, which is just these two, r plus and r minus multiplied together, and then the appropriate numerators. This one would be r plus r minus in the denominator and have an r minus up top, and this one would be r minus r plus in the denominator and have an r plus up top. So there you go. That's just finding the common denominator and then adding those two together. And notice from this we have a negative here. Now I need to work with getting something that I can work with here. And what I'm going to do is to recognize that this r minus minus r plus is the same thing as, whoa, biggest drawing tool ever. That distance there is going to be r minus minus r plus. My apologies. That this distance minus that distance is going to be this distance to the difference in the two is going to be that one there. But then I need to recognize that for a if r is much bigger than d, and I won't try to write that for you, but r is much bigger than d, then this r plus times r minus, well, those two become essentially the same as this value here if you go far enough away. Oh, this is going to be very awkward. Okay, let's make the picture fit. Now we'll drag that back. Still does not fit. I tell you what, let's rotate this guy, but I can't because you're in the front. Go to the back. Okay, now I can grab this one, we'll rotate it, and something, rotate too much. Okay, so that distance from the center of the dipole out to where the thing is, which we would call the distance from the dipole. P is r away from the dipole, that if there is a location which is identified with the dipole, it would be the middle here. But that vector quantity, the position vector of P relative to the dipole, and the dipole moment, which I hope you remember, a lowercase p, and the direction of that vector, the dipole moment vector, is given by the direction of the that a positive charge would be pushed outside of the dipole, that angle between those two is equal to theta. And there was theta, and it went away when if I pull this out of the way, there you can see theta again. And theta always, when we talk about the angle between two vectors, this would be identified with the dipole, and there's the distance from the dipole. Always you put the two vectors together tail to tail. So there is theta. But wait a minute. If that's theta, and we're far enough away, this is also theta here. And so this distance, r minus minus r plus, is equal to the hypotenuse times the cosine of theta. And here it is, that the potential would be the 1 over 4 pi epsilon times the charge of the dipole, and for r minus minus r plus I put in the distance cos theta, and for r minus times r plus I put in r squared, and there you have an expression for the potential for a dipole when you are a distance r away from the dipole. But of course d times q is equal to the dipole moment, and so I can also write the expression like that. This is worth memorizing. There is the potential for a dipole, where theta again is the angle between P and R. I would ask you to recall, I'm going to have to get rid of you guys. You go away. We'll just delete everything. Yes, go away. Thank you. I would ask you to recall that the field of a dipole, and this time it was only on the axis, was given by this quantity, which we also need to memorize. But note, the potential is equal to the integral of the field dot ds. And if you take this expression and integrate it with respect to z, you have z to the minus 3, which is going to become z to the minus 2. There we are. And then, with that z to the minus 2, you're also going to have to multiply by a negative 1 over 2 out front. And when you multiply this by a negative 1 over 2, you get this 1/4. So you could get, if you could memorize this one, then you could get to v by integrating this with respect to z. Or you could also get to v by the development we just went through. But one way or another, I guess the third option is to just memorize it and not be able to get there at all. That then concludes this lecture.